Hi and welcome to our next Level 2 Calculus videos. There are two parts to this video, Part A and Part B on kinematics. One is to do with differentiation and one is to do with anti-differentiation. Again, I get a little excited here because this is another really good use of seeing calculus and algebra in the real world. All right, kinematics is the study of motion. We can express the velocity, which we call v, as the rate of change of displacement, s, with respect to time. In other words, velocity is the change in speed over the change in time. Now we use s for displacement, which means distance. I know you're going to get a little confused here. You prefer to use d for distance or displacement, but we don't, because if we did, when we use calculus, would have dd over dt, and that just doesn't really make a lot of sense. So we use s for displacement instead. We can express acceleration, which we call a, as the rate of change of velocity, v, with respect to time. So acceleration is the change in velocity over the change in time. We could sum all that up. If that was a little bit complicated to get your head around, we'll sum it all up with this cool diagram. If we have displacement, which is just distance, and we want to turn it into a velocity function, we're going to differentiate. If we have a velocity function and we want to turn it into an acceleration function, we differentiate a second time. If we had an acceleration function and we needed to go backwards, we'd anti-differentiate and would have to anti-differentiate back to a displacement function. So this diagram here, really, take a photograph, a picture of that, and get your head and brain into that, sums up the whole kinematics that we're going to talk about. All right, we've got one example and three different parts to solve. A spacecraft's moving through space in a straight line. The rockets are ignited at 12 a.m., which is midnight, on the 13th of July 2009. From this time, the distance traveled by the spacecraft is given by the following formula. S is equal to 10t plus 0.5t squared, where S is measured in kilometers, t is measured in seconds. Right, so part A, what is the velocity of the spacecraft at 1 o'clock in the morning on the 13th of July? Well, we just talked about if we have a displacement or distance formula, we can differentiate it to get the velocity formula. So we're going to differentiate this function to get velocity. Right, so let's differentiate it. The 10t differentiates to 10, and the 0.5t squared, the 2 comes out the front and times is by the 0.5 to get 1t to the power of 1, which is just t. Now that was a little bit, whoa, I just got lost there. You wouldn't have any hesitation if I gave you y equal to 10x plus 0.5x squared, which is the same formula, but instead of an s we use a y, and instead of t we use x. So just practice using differentiation with different letters. Right, so this is our velocity formula, 10 plus t. Now, we're told what's the velocity 1 o'clock in the morning? Well, 1 o'clock is 1 hour after the rockets are ignited. So we need to stick 1 in for t, for time, 1 hour later. So we just need to go 10 plus 1, which gives us a velocity of 11 kilometers per second. Right, part B, what's the velocity at 8:30 on the 13th of July? Well, we've already got our velocity formula. We did all the hard work in part A, so we just need to work out that 8:30 is 20 and a half hours after midnight. So we just need to substitute t as 20 and a half, and that gives us a velocity of 30.5 kilometers per second. Finally, part C, what's the acceleration of the spacecraft? Well, we've got our velocity rule, which we worked out in part A, 10 plus t, which is 10 plus 1t, and we need to differentiate again to get acceleration, and that differentiates to 1 because the 10 disappears and the 1t differentiates to 1. So the acceleration is 1, and if you want to know the units, it would be kilometers per second per second. But don't get caught up in units. You're not going to get marked on units. Great. Thanks for watching.